and welcome again to the multimedia course. Today we continue the flow of our chapters and of our topics, and we arrive at the video coding, and we will see video coding standards including MPEG. So the current chapter title is Video Coding Standards, and it is based on the chapters 10, 11, and 12 from the textbook. In this chapter, we will see 7 subsections going from basic video compression techniques to video compression with motion compensation, which is a concept that we must understand because it is used in the different coding standards together with the techniques for searching for motion vectors. So these two concepts will be explained. And then we will start by understanding what are the standard committees, why there are more than one standard committee, and what are the compression standards. Among those compression standards, we will see closely the H.261, H.263, the MPEG video coding 1, which includes also the MPEG video coding, which includes MPEG-1 and MPEG-2, and finally the new coding standards, which are H.264 and the latest H.265, or what we can call MPEG-H, which is also based on H.264, which is MPEG-4. So let us begin our lesson. This will be a very interesting lesson and a very easy one. Let us begin by the first section, basic video compression techniques. To understand the compression techniques, let us introduce why do we do video compression and how. So as you can see in the figure, a video consists of a time-ordered sequence of frames. In this representation, we extracted frames, sequential frames from a given video. Here you have the little girl, you can see in grayscale, approaching from the tree, and in the frame n+3, the tree is now behind the girl, so the girl is moving throughout the video. As you can see, this is a time-ordered sequence of frame. If the girl is moving forward, she will continue to move forward in a certain lapse of time. So in a certain interval, the action can be predicted. We say there can be prediction. So an obvious solution to video compression is the predictive coding based on previous frames. Instead of coding each frame alone, since we know now that they are related in time, they are correlated, we can base on a previous frame in a certain video in order to code a current frame. How? The compression can proceed by subtracting images. So I can, for example, begin using a certain image n at time n, order n. And then for the next one, I subtract the frame +1 minus frame n instead of coding frame +1 as if it were an image, an independent image. So subtract in time order and code what to code, not the image, but the residual error. So this can be done even better. How? By searching for the right parts of the image to subtract from the previous frame. So instead of working with all the image and all the next image, I can take parts from the image and search in the previous one where does the square, for example, this white square best fit, and then I subtract these two subparts, or what we say sub-blocks or macro blocks, from each other. Because the girl is moving, the convenient block is not staying at the same indices. So I will search for the right block in order to minimize the residual error. Why do we want to minimize the residual error? because as we have studied in the compression techniques, if we have lots of zeros, we can use lossless compression algorithms in order to code and to higher the compression ratio. So what we say, the consecutive frames in a video are similar, and this is the temporal redundancy. This is due to the similarity in the consecutive frames. So we repeat, not every frame needs to be coded independently as a new image. So we have to code the difference between the current frame and other frames. Other frames may be previous or later frames. And this will lead to small values. With small values, we have low entropy. With low entropy, we can achieve higher compression ratio. So this is very good for the compression. So what are the steps of video compression based on motion compensation? This is what we call video compression based on motion compensation. We will first do the motion estimation. What is the motion estimation? It is to search for the motion vector. Here, for example, from frame n to the frame n+1, the girl advanced a little steps. So the block that indicates the face of the frame advanced a little bit. So what I just drew in red here is called the motion vector. So it is to indicate that the face, the block I have to code now in the frame n+1, was in the previous frame has moved this much. So this is the vector here. Once you have estimated the motion, you know what is the motion vector. It is +2 lines, +3 columns, etc. You do the motion-based prediction, and after the motion-based prediction, you derive the prediction error, which is a simple difference between two matrices. How do we do these three steps? We will see now in the next slides. So here in this slide, I will explain a simple motion example. For this simple example, I will use a very primitive graphic here, but this is explicit, simple, for you to understand the concept. So let us explain here. Consider a simple image block of a moving circle. So we have a very simple frame in which there is a circle. Instead of the girl, we have a circle. So the present picture, the circle is a little bit to the right, but the previous picture, the circle was centered in the middle. So according to the previous picture, we can deduce here that the circle advanced a little bit to the right. So let us just consider the difference between the two frames. So I take the present picture, the current frame, I can say, and I have the previous frame, and I can simply subtract the two matrices, a matrix minus the other. So I will obviously have here what we call the difference picture. As you can see, the difference picture contains a lot of zeros. This is the color black here. So here we are considering a very simple binary image with 1 for white and 0 for black, and the difference is contains a lot of black because there is a lot of 1 minus 1, and there is eventually 0 minus 1 and 1 minus 0, so in absolute value we have some whites. So this is called the process to obtain the difference picture is called the encoder. Suppose now that I sent to the coder the previous picture and I didn't send the present picture, I sent only the difference picture. Can I obtain the present picture if I am receiving the pictures one after the other? If I received the previous picture and I received the different picture. Can I reconstitute the present picture? Yes, it is simply the addition. So in encoding, you do the difference, and in decoding, you have the previous picture, you obtained it somehow, because this is recursive, and then you have the different picture, so you can decode easily and obtain the present picture and render it on the screen. So suppose this decoder is to render on the screen. So why do we do that in the first place? We do that because instead of sending the present picture and the previous picture, this will cost us high calculation. We send previous picture and difference picture. As we have said already, this contains lots of zeros, so this has low entropy, and this will make a better compression technique. So now we will continue with our example, and let us explain that we didn't only do the difference as in this slide, let us do some motion estimation. So in the previous slide we didn't explain the motion estimation, now we will explain it. As you can see in this graphic, there are our actual picture, and here is our previous picture. In the previous picture, the ball was a little bit to the left, and the ball advanced to be a little bit to the right. How do I code this? Instead of making the difference as in the previous example, look at the difference. We have lots of zeros, but we have also lots of ones. We want to make those non-zero values closer to zero. So what do? We do the motion compensation. So we are explaining here the motion compensation. We obtain this vector. This is called motion compensation, MC. We will be referring to this notion very frequently during this chapter. So we calculate the motion compensation. So we will search in the image, in the actual picture, by reference to the previous picture, where this ball was, in which part of the image, and how many pixels it moved. So we will deduce the motion estimation. This is the motion compensation, and now we have the motion compensation. After I apply to the previous picture the motion compensation, so I can deduce where the ball is now. After the application of the motion compensation, I do the difference picture. So in this example, the error is very much smaller, because I already estimated the motion. So I have a smaller difference picture that can perform better in the encoding. How does the decoding now applies? Simply, you have the difference picture, you have the previous picture, and you have the motion compensation. So you take the previous picture, you apply the motion compensation, you deduce the motion compensated picture. This is not the exact actual picture. You have to add the different picture to it, but after adding the difference picture to it, you will obtain your actual picture. So let us recapitulate. You have previous picture. You don't want to send your actual picture. You want to send a difference picture, but before making the difference, you will estimate the motion. You have this now actual picture, but you don't want to send it. You do calculate. Now in the next slides we will explain how we calculate the motion vectors. When we obtain the motion vector, we apply to the previous picture, we will obtain the previous picture motion compensated. This picture also we will not be coding, we will only be coding the difference between the actual picture and this one. So we will be coding only the difference picture and the previous picture and the motion estimation. so which will give us, of course, the motion vectors. So we take previous picture, motion vectors, and difference picture. The decoder receives them, as you can see now here. Motion vectors received, difference picture received, and previous picture either received, either already decoded. So he takes them, he applies the motion vector, the motion compensation on the previous picture. He calculates the compensated image. We add the difference picture to it, so we decode the actual picture. This is called the decoder. So that's why we use simple graphics, so that you can understand that the final goal is just like we encoded, we can reconstruct the actual picture without sending it. The motion compensation work. The image will be divided into macro blocks. We will not be working on the whole image because it is not like the simple example we just saw. It is not consisting of only one ball that has moved, and the one ball we cannot predict alone. So we will divide the image into macro blocks, MB, capital M, capital B, of size n times n. And this n is a variable, but for usually we take n equals 16 pixels for luminance by default and equal to 8 pixels for chrominance. Why we take smaller macro blocks? Because don't forget that we have already applied macro chroma subsampling. So chroma subsampling, for example, 420. So already the three matrices for each image are not of the same size. The chroma matrices are quarter the size of the luma matrices. So if we take greater macro blocks, the equivalent macro blocks for the chroma, for the same objects, for the same image space will be of size 8 by 8. So we divide into macro blocks, and then we apply the motion compensation. Remember this term MC to say motion compensation at each macro block level. So I will search for each square, each macro block, where it will become in the target image. So I have a reference image, as you can see. I have a reference image. I call it RI or RF to say reference frame. I have a target image that I am now currently coding, and in my target image divided into macro blocks, for each macro block I will search where was this macro block in the reference frame. So at each macro block, the target frame or target image is the current image. The reference frame, or we can have more than one reference frame, we will see later in this chapter how, is the previous or the future frame. So we take a reference frame. For now, keep in mind, let's suppose this is the previous frame. And the motion compensation is to search for a match between the macro block in the target frame and the most similar macro block in the reference frame. How do I know what was the most similar macro block in the reference frame? I have to search for it. I take one macro block, suppose here in the target frame, the macro block that is in bold. I have to find that it was here. How do I find that it was here? I have to search all the macro blocks, even not in units. I have to search them sequentially, for example, and to obtain the motion vector MV. What is the motion vector? As you can see on this image, it is how many pixels in horizontally and vertically do I have to move in order to say that this macro block was here in the reference frame. So the motion vector is the displacement of the reference macro block to the target macro block. So in case the reference frame was a previous frame, we say this is a forward prediction, that We know now what we have an image. We can tell next what will happen. I know now that the ball moved a little bit to the right. I can predict, for example, for the future, for the forward prediction, what will happen with the ball next. And the backward prediction is to accomplish motion compensation but referring to a future frame. You will say, how do I do this? Remember that you have all the frames, and all what you do is coding the frames. So you have the frames, you know what happens, but you want to code. Instead of sending each frame alone, you are sending the prediction. So this is called backward prediction. So macro block vectors, macro blocks and motion vector and video compression, how it is done. Let us understand our slide here. So let us recall the terms. This is the reference frame, and this is the target frame, and this macro block is the macro block I am coding right now. Okay, I want to know what is my target here. I want to deduce the motion vector, the MV. This is my target in this image. How do I deduce the MV? By reference to the reference frame. Okay, MV search is usually limited to a small immediate neighborhood. Why? Because we say if the ball in the reference frame, if this part of macro block was not exactly where it is now, look here, now it is on the index I, ordinate J, index X, ordinate Y. If it is not here now, it must not be very far, because this is a time-ordered sequence. So it cannot disappear from this region. It was either on the left, on the right, on top, and on bottom. So we will limit the search inside a window, both horizontal and vertical displacement. We will take a variable P. We will search only by reference. This is the center of the block, x0, y0. We will search only plus P, minus P on horizontal axis, and minus P plus P on vertical axis. This will give us this window. So I will search for the center of the reference block inside this window. If I don't find, I don't find. So for example, here I found it. This is the center of the reference macro block. So this is the matched macro block. Okay, now I will see how do I search, but in this frame, in this slide, I'm only setting that we have to do the search in a window of size 2p plus 1 times 2p plus 1. So let us erase this slide and see if we covered all the concepts that are mentioned here. We have the match macro block, we have the search window, we have explained the macro block, the target frame, and the reference frame. We know that each macro block is of dimension n times n. It is located on xy, where the center is x0, y0, and finally, on the reference frame, I take the x0, y0, and I subtract P and add P on both dimensions to search for the matched macro block. So how do I do the search for motion vectors? How do I do the search? In fact, I take all the macro blocks in this window, all the centers will constitute all the macro blocks in this window, and for each macro block I will see the difference between the two macro blocks that is measured not in difference, not in the sum of the matrix after the difference, but in what we call the measure that we will be using is the mean absolute difference, MAD. The mean absolute difference is a simple double summation of the difference between the current and the reference pixels, corresponding pixels, on both dimensions, and divided, normalized to the size of the macro block. So it is, for example, the first one minus the second, the corresponding pixel. For example, here, this, let me write, use the pen, this x minus this x in absolute value plus this circle minus this circle in absolute value, and so on to finish the line, and then the next line. So double summation, that's why we use double summation always, and in absolute value, and normalized by the size of the block. The goal of the search is to find a vector ij, so this is called mad ij because the center here was not the same. Okay, here we have moved, this is ij, the coordinates here, and the goal here is to find the vector ij that gives me the minimum mark. So for each candidate macro block I am searching in the window, for each candidate macro block I will calculate MAD. Which is the macro block that I will say this is it, this was here, the one that will give me the minimum MAD. So I will use it, it will be of coordinate ij. So the UV, the motion vectors coordinate, are the ij's that gave me the minimum MAD simply. As we have said, I cannot search in all the frame, I will search only in a search window where I can vary between minus P and P and J between minus P and P. Supposingly, as I always go back here to show you that this is x0, y0. So if you don't move, you will find the macro block at its place. If you don't find it, you search in you cover all the search window. Now, the question here, how do I search in all the search window? So we will see how to do this. Okay, the three methods to search the window are the complete search one, the sequential search. Another way is the 2D logarithmic search. So this will reduce into, instead of n to the power 2 into log of n. And the third method is the hierarchical search. For the sequential search, as you know, we have to sequentially search the whole window in reference frame, and this will cost us 2p plus 1 times 2p plus 1 macro blocks to compare with our macro block, and this will cost us 2p plus 1 times 2p plus 1, of course, MAD calculation in order to deduce which is the minimum. So this is called also a full search, and in this full search, as you can see, a macro block is centered at each of the positions with the window is compared to the macro block with the TF using MAD, and the vector ij that offers the least MAD is designated as the motion vector UV for the macro block in the TF. It is very costly because it is a complete search, and the algorithms is the following. Begin, initialize the minimum to a large number in order to find quickly the minimum, and for I going from minus P to P, for J going from minus P to P, current MAD equal MAD of IJ. Here MAD of IJ is a function that simply do the double summation over n2 of the absolute value of the difference. If the current MAD that I just calculated is less than the minimum, then this is the minimum. If this is the minimum, so the ij that I am now calculating are the motion vector. I am searching after all for the motion vector, but so get the coordinate u equal I and v equal j. Else continue the search and do the full search. At the end, return the motion vectors. So this is the algorithm for the sequential search. As you have already seen, there are better algorithms. One of them is the 2D logarithmic search. How do I accomplish the 2D logarithmic search, which is a cheaper version, but it is suboptimal. It may not find the optimal solution, but it will find a suboptimal, but it is an effective solution because it does not cost in operations. How do I accomplish this technique? So I do several iterations, just like the binary search. I initially cover only 9 locations. Where are those 9 locations? Here, the location 1 that are marked with 1. So initially, of course, I will search for the macro block in the initial coordinates where it was before, and then I will search for it. I will go a step lower, a step to the right, a step to the left, and a step to the diagonal. So I search for it in the 9 location marked 1 here on the figure. Between those 9 locations, I will see which is the minimal MAD. For example, in this representation, I had this one in gray, the minimal MAD. I search for the MAD. The one that yields the minimum MAD is located, so I move the center of the new search region and I reduce the step, which is the offset, to the half. And now I will search in 9 new locations, but the offset is reduced to the half. So I will search on a finer space, and in the next 9 iterations, the next 9 new locations are marked as 2. Now I will search in the locations 2, and between those locations, the one that gives me the smaller MAD, I move the center of the search to it, and then I reduce the step into the half and I search again, and so on. So this is the 2D logarithmic search. Another kind of search is the hierarchical search, which is a similar way. How do I accomplish this? You can benefit from a hierarchical search, which is called also multi-resolution approach. You initially estimate the motion vector for reduced resolution of the image. You first reduce the resolution, you estimate the motion vector, then you go to the upper resolution and you find that you tune the motion vector. So you estimate again, but you know now where it can be, so you have located it using the reduced resolution, and then you continue. So this is just like the 2D logarithmic search. In this example, you have a 3-level hierarchical search. The original image is at level 0. Levels 1 is downsampled by a factor of 2, so the image is quarter the original. Level 2 is also downsampled by a factor of 2, so it is the quarter of this one. And then you accomplish the initial search on the level 2, and then you go up to search for the motion vector again and again. So the size of the macro block is smaller, the P is proportionally reduced, of course, and the number of operations is greatly reduced. To prove that, we will take an example, and in this example we had done a comparison of the 3 search approach: the sequential, the 2D logarithmic, and the 3-level hierarchical search. We took 2 examples for P equal 15 and for P equal 7, and we calculated the number of operations for a video with a frame size 720 x 480 and with 30 frames per second. Okay, for this video, how many operations per second I had to accomplish if I use sequential search it is 30 times 10 to the power 9. If I use 2D logarithmic search 1 times 10 to the power 9, I reduced the number of operations by 30. And if I accomplish using the third technique, which is the 3-level hierarchical search, it is half 10 to the power 9. So this is 60 times less. And another example is for a smaller p. When you, of course, reduce the search window, you will reduce the number of operations. So instead of 7 times 10, it is reduced 10 times this time, and so on. So this was how we do. Now we will see the compression standard committees and the compression standards. The compression standard committees, image, video, and audio compression standards have been specified and released by two main groups, and we already mentioned these groups in previous chapters. So the first one is the ISO, the International Standard Organization. It has released the JPEG and the MPEG standard, but it is not alone in the field. There are also the ITU, which is the International Telecommunication Union, which has released the H.261 and H.262, H.263 until H.264, and this is a very important also standards. Also, you don't know them, but we will study them and you will see that the MPEG is based on them. And this ITU has also the CCITT, which is the Comité Consultatif International Téléphonique et Télégraphique, whose parent is ITU, that also contributed in the standard and the compression standard for the video. So whilst in many cases one of the groups have specified separate standards, so either ISO alone does a standard or ITU alone does a standard, but there is some crossover between the groups. The groups were not independent, so the groups were not isolated. They saw what each other does, and they adapted and they took the advantages of each other until lastly they have joined their effort. Okay, they have joined their effort. They said, why do we work each one alone? Let us do the standard together. So this is a timeline table that shows you how they evolved together. So first, the ISO, as we have studied in the previous chapter, released the JPEG standard in 1989. The ITU likes the standard, so it adopts it and it called it T81. Then the ISO began on working on the MPEG on 1991. The H.261 released in 1993 based on CCIT, which is released on 1990. So you can see that before the MPEG was released, already the ITU was working on a draft that is earlier. So the MPEG is based on the H.261. Then you had the H.262, known as the MPEG-2. And then in 1996, you had the H.263 extended as H.263 plus, H.263 plus plus. The ISO committee, the ISO standard committee, did not sleep meanwhile. In 1998, it releases the MPEG-4, and then the MPEG-7, of course, in 2001. And meanwhile, also, the ITU released the H.264. That was for the DVD quality. That is now also a part of the MPEG-4. It is now part of the MPEG-4. And finally, in 2013, they said we will join our efforts, and they had this final product, which is called in ISO MPEG-H, and in ITU they call it H.265. So let us see these standards. What happened? Now we know the motion compensation, we know the motion estimation, we know how to calculate the motion vectors. Why did we learn this and how they were used? So in this section we will study the H.261 and H.263. So let us study the H.261. What is this? This is an earlier digital video compression standard. Its principle of motion compensation based compression is retained in all later video compression standards. So this is the standard that introduced the motion compensation we just explained in the beginning of this chapter. So with motion compensation, we take advantage of the temporal redundancy in the video frames. So this standard, why it was designed? It was designed for video phone, for video conferencing, and other audiovisual services over ISDN. So we had before Zoom and Microsoft Teams video conferencing, but with very low rates. So video codec supports bit rates of p times 64 kilobits per second. You have to make the coding that to be able to pass in a multiple of 64 kilobits per second. Okay, so the why we have this constraint, because this is video conferencing. So the other person that is talking to you on video conferencing must be able to hear you and see you in real time. To be able to do this, the coding, the compression, and the decompression, the coding and the decoding must be in real time. So you must make the data enter in a less than a certain p variable that can be 1 to up to 15, for example, 15 times 64 kilobit per second for decoding and encoding, where p range from 1 to 30, and this require a delay of less than 150 millisecond, so that the video can be used for real-time bidirectional video conferencing. You have to see your partner, and your partner must be able to see you. So this is bidirectional video conferencing. So there is coding and decoding from both directions, from the two directions. The H.261 is a standard that belongs to the family of the ITU recommendations. Now you know that H.261 was released by ITU, but it is not an orphan standard. There were other standards for example, H.221, H.230, H.242, each one for a certain purpose. What are the video formats supported by the H.261? As you can remember from the chapter of video, we have those formats, the Q-SIF, which is the quarter of SIF, half the number of lines, half the number of columns, and this is the chrominance image resolution, also subsampled, chroma subsampling. So also you have here half, and this is for the luminance, and this is for the chrominance, and the bitrate is 9.1, and it is required that to be supported by the H.261. However, the SIF, which is a larger video, if you have the H.261 standard, it is optional for you to support the transmission of this video. Of course, a video of type SIF is a bigger resolution than the one of type QSIF. So let us talk now about the frame sequence in this standard. Now we know what is the motion compensation. Let us talk about the frame sequence. We said that we will take advantage of the temporal redundancy. But do we code the difference between the images until the end of the video? So we code the first image and then only the residual error and the motion compensation. The question here, what if there is an error into the transmission? You remember, if you are viewing a certain video and some frame came erroneous, what happens? Do I have to lose all the rest of the movie, or do all the image in the video conferencing, all the subsequent images? No, there are two types of image frames that are defined in the frame sequence in the standard H.261. What we call the intra frames and what we call the inter frames. The intra frames are called short iframes. They will be treated independently. So they will be treated as they are a JPEG image. No relation with the previous frame, no relation with the future frame, no advantage taking of the temporal redundancy. So these are treated as independent image that on which we apply the transform coding method, the DCT, just like the JPEG, and the spatial redundancy removal. Okay, we remove the spatial redundancy but not the temporal redundancy. On the other hand, we have the other type of the frames, which is called interframes in relation to each other, the frames to each other. The P frames are not independent. We use the forward prediction coding method from a previous either P or either I frame, and this is in which we, of course, make a temporal redundancy removal. Okay, to avoid the propagation of coding errors, an iframe is usually sent a couple of times in each second of the video. So each second I send an iframe which is independently coded. If something bad happened previous to this frame will come as an absolute value, and the decoding continue from here and on independently of the past. So the motion vector in H.261, look here, the motion vectors in H.261, you remember we searched inside a search window in units of full pixel with limits of plus or minus 15 pixels. So P will be equal to plus or minus 15 pixels. So the search window 2P plus 1. And you cannot find a motion vector, let's say 2 pixels and a half in horizontal and 5 pixels in vertical. You cannot have decimals over the pixels. So you take the pixels in full units. This is it. Why do we mention this? Because in later versions of coding standards, we can have decimals over pixels. Now this is the image that represents the frame sequence. As you can see, you have an iframe. Okay, in these iframes, they are coded just like in JPEG. We don't code the relationship between the frame and the next one or the previous one. And then you have in between the P frames. The P frames are coded relative to each other. Relative to one, for example, this P frame was not coded independently, it was coded relative to the I frame. It means I did the motion estimation and I sent only the motion vector and the differential error. I sent the I and then I sent the MV and the difference error. And then this P, this one, having the previous P decoded, I also code it depending on the previous P, and so on. But the I, look here, we don't have an arrow. The I is sent entirely. It is sent in the sequence entirely independently of the previous frames. So, as we said, we have intraframes and interframes. For the intraframes, iframe, what is the coding? The coding is the exact coding as in the JPEG standard. You take the frame, you do the subsampling, you cut into blocks, and for each 8x8 block you apply DCT, then quantization, then entropy coding, of course zigzag reading, and then entropy coding, and so on. So you take the macro blocks, 16x16 for the Y, but 8x8 for the CBCR channel, since you have the chroma subsampling. Those are, a macro block consists of 4 Ys, 4 8 times 8y, 1 8 times 8 block CB, and 1 8 times 8 block CR. This is one macro block. For each 8 times 8 block of this type, I apply DCTs and quantizations and entropy error. Of course, zigzag scanning and then entropy coding. What about the interframe predictive coding? As we have just explained, you for each macro block in the target frame, you have to calculate a motion vector. A motion vector is allocated by one of the search methods discussed earlier, either sequential, either logarithmic, either hierarchical, but you obtain finally your motion vector. So this is it. Let us say this is the target frame. Now you are coding for a certain macro block. This is the current macro block you are coding. You obtain the motion vector. You obtain the motion vector by one of the techniques. So you will have the best match. You then apply the difference. You have the difference macro block. Not like the previous intraframe coding. Now you code the difference macro block and not the macro block itself. Let me change the pointer options. Let me change the color. I take now the green color and I will mark here that for the difference macro block I will apply the following. I take the each 8 by 8 macro block. I have 4 for Y, 1 for CB, 1 for CI. But remember, I have lots of zeros because this is only the difference. I apply for each of the 8 times 8 block the DCT, then the quantization, and then the entropy coding. And also I have the motion vector. For the motion vector, I also apply entropy coding, and then I obtain the predictive interframe coding. So for each macro block, then a difference macro block is derived to measure prediction error. Each of these 8 by 8 blocks go through the DCT, quantization, zigzag scan, entropy coding procedures. Next, the P-frame coding encode difference macro block. We say here MVD, not MV, not the difference macro block, not the target macro block itself. Sometimes a good match cannot be found. Sometimes you search all the reference frame for a certain macro block, you cannot find it. So in this case, you may find all the other macro blocks of the target frame, but one of the, for example, you have here a bird that was not present in the previous reference frame. What do? So the prediction error exceeds a certain acceptable level. You cannot say this is the best match. So the macro block itself is then encoded. You take the macro block, the special macro block that for which you didn't find a certain prediction acceptable, and you code it as if it were inside an intra-frame, as if it were a macro block from the previous procedure in the previous slide, as if it were here. And this will be termed as a non-macro block, non-motion compensation macro block. For a motion vector, the difference motion vector is sent for entropy coding. So also for the motion vector, the motion vector difference is equal to the motion vector preceding minus the motion vector current. Okay? And that's why entropy coding will also be fine. For the H.263, which is an improved video standard for the video conferencing and other audiovisual service transmitted in public switched telephonic network, this is an improvement of H.261, and as you can guess, we want a higher video resolution. We want to do video conferences, but we want a bigger compression because we want bigger resolutions to bypass the rate. This is the format, video format supported by H.263. You can see you have the smaller, you have the sub-QSIF, but you have also the bigger video formats, which are the 4CIF and the 16CIF. And the bit rate has augmented, so you have now 64, and you have a multiple of 64, 256, 512, and 1024. Next, we will study and we will see together the MPEG video coding, which is done by the ISO. And the MPEG video coding, and especially the MPEG-1, 2, 4, and 7. Overview: the MPEG, which is Moving Pictures Experts Group, was established in 1988 for the development of digital video. And of course, it is appropriately recognized that the property interests need to be maintained within the family of MPEG standards. They have already the JPEG, the ISO, and they want to maintain the standards within the family. So, this standard was accomplished by defining, by defining only a compressed bit stream. So, the standard defines the compressed bit stream, which implicitly, you have to know how to decompress it. That implicitly defines the decoder. So if you have a certain format for the compressed bit stream, you are obliged to do the decoding in a certain way. And this way, the compression algorithm itself, they don't define. The MPEG, it does not define it, and thus the encoder, it does not define it. But since you define the compressed bit stream, you are obliged to do a certain the things in a certain way to obtain this compressed bit stream. But the compression algorithm and the encoders are completely left up to the manufacturers. So each manufacturer that say I can provide I am following the MPEG standard, you know that you will have the same compressed bit stream. You know how to decompress it, but each one will do the compression on its way, but accordingly to the definition. So the MPEG-1, to begin with, is the first of the family, adopts the CCIR 601 digital TV format known as SIF, Source Input format. It supports only non-interlaced video. Remember this, MPEG-1 does not support interlaced video. And the picture resolution was designed for around 350 to 3300 pixels. It differs a little bit because NTSC and PAL differs in the ratio and in the number of frames per second. So MPEG-1 supports these things, and it uses the 420 chroma subsampling. MPEG-1 is also referred to as ISO IEC 11172, and it have inside it 5 parts, which are the first for the system, the layer 2 for the video, the audio. That's why we say MP3, because it is MPEG layer 3, and 4 for the conformance, and 5 the software. Let's talk now about the motion compensation in MPEG-1. In reference to H.261, what does MPEG-1 provide us? What does it contribute? How does it contribute to the standardization of the video coding? Motion compensation, MC, means motion compensation based video encoding in H.261 works as follows. So now we are going to remember how do motion compensation work. In motion estimation, each macro block of the target frame is assigned a best matching macro block from the previously coded I or P frame, and this is called prediction. We already explained this. The prediction error, what is a prediction error? Recall, this is the difference between the macro block and its matching macro block that we found in the motion compensation, sent to the DCT and its subsequent encoding steps, of course. This is the forward prediction. The forward prediction, as we have already explained also, this is a prediction that is from a previous frame. Why we have the need for bidirectional search? The MPEG-1 says you need a bidirectional search. What is a bidirectional search? Let's consider this example. So this is our target frame. Okay, let us examine this target frame. What happens here? You have the wall, you have a certain structure, and you have a ball. If you are interested in this particular macro block and you want to deduce where it was in the previous frame, can I find it? No, I cannot find it. So the macro block containing a part of a ball in the target frame cannot find a good matching macro block in the previous frame. There isn't, because half of the ball was occluded by another object. So, how do I code this macro block? In H.261, remember we said if we don't find an appropriate macro block, we will code it as if it were an independent intra-frame macro block. So, as if it were a macro block from a JPEG photo. But the MPEG-1 says if it appears here and it does not appear in the previous frame, there is a great hope that it will appear in the next frame, because it will not, because since this is a video, this is a ordered sequence of frames, it does not make sense to appear into only one frame, because one frame is 1/30 seconds. This is nothing, nobody will see it. So this is the basic idea. Since you have all the frames and now you are doing the coding, if you cannot match from previous one, you can match from the next one. The only trick here is when you have to code, you code the previous frame, you code the next frame, and then you code the target frame, because the target frame will be relying on the next frame and on the previous frame. So a match, however, can readily be obtained from the next frame. So this is the main idea. So the motion compensation in MPEG-1 introduced a third frame type, which is called the B frames. We know the I frames, we know the P frames, and now the MPEG-1 introduced the B frames, bidirectional frames, and it's accompanying bidirectional motion compensation. How we do motion compensation now? You have the target frame, you have for each macro block, the target macro block. You will search for the macro block, for the corresponding macro block from the previous reference frame and from the next future reference frame. You will have two motion vectors, okay? So you will have two motion compensation, each from the directions. So you will do the averaging of these motion compensation, A, V, G. You will do the averaging of these motion compensated macro blocks, and then you do the difference. So you obtain the difference macro block. You obtain one difference macro block, of course, and then you continue normally DCT, quantization, entropy coding, and you have the two motion vectors that will also follow the entropy coding. Remember here there are two motion vectors. So let us read. Each macro block from a B frame will have up to two motion vectors, one from forward plus one from backward prediction. If the matching in both directions is successful, so if the, for example, if the MAD measure is acceptable from both directions, so the matching from both directions is successful, you have two motion vectors, the two average motion macro blocks generated, and then you generate the prediction error. If an acceptable match can be found in only one of the reference frames, if the future is not good for prediction or the previous is not good, no match adequate is available, so in this case you continue as normal as in H.261. You code only one motion vector and its corresponding macro block. Okay, so this figure is the B-frame coding based on bidirectional motion compensation. And the frame sequence is now the following. You have I frame, each time you have I frame to code independent frames. And then you have the P frames, the usual P frames, but in between you can benefit from the B frames, which are bidirectional, which profit from the previous and future frames. So this B frame depends on the I that is previous and on the P that is next. On the P, not on the B, because B's do not depend from each other. Why? Because you have to code. How do we code? This is the display order, but what is the coding and the decoding order? The coding and transmission order is that you send the I, you send the P, and then you send the two B's. Why? Because the bidirectional frame depend on the I and P. So you have to send the I and P on which they depend before you decode them, and so on. This is the MPEG-1 constraint parameter set. As for the major differences with the H.261, they are the following. Instead of groups of blocks, as in H.261, an MPEG-1 picture can be divided into something called slices. This is slices in MPEG-1 picture, the white, the gray, the dark, etc. The slice that can contain variable number of macro blocks. Okay, they may also start and end anywhere as long as they fill with the whole picture. And each slice is coded independently. Additional flexibility in the bitrate control, and the slice concept is important for error recovery. Other major differences between MPEG-1 and H.261 is the quantization. MPEG-1 quantization uses different quantization tables for intra and intercoding. So for intracoding, it uses tables such as the following in Q1 table, and for intercoding, it codes them over this is the default one, a constant table. And this is the formula for the intra mode, which gives the rounding, and the inter mode is the lower bound. So this is also a major difference between MPEG-1 and MPEG and H.261. The typical size of compressed P frames is significantly smaller than that of I frames, and you know that. We can ask this as an exam also, because temporal redundancy is exploited in interframe compression. Now, also the B frames are even smaller than the P frames because of the advantage of bidirectional prediction. So with bidirectional prediction, you can accomplish a smaller error difference, and lowest priority is given to the B frames. So lowest priority is given to the B frames, so quantization is bigger in the B frames. So typical compression performance of MPEG-1 frames, the I frames is compressed on the compression ratio 7:1, the P frames 20:1, whereas the B frames is 50:1. So the B frames are really very, very compressed, and the P frames also. In average, the compression ratio is 27:1, which is gives the size of 4.8 kilobytes as a compression. layers of MPEG-1 video bit stream. You now have a video sequence. In each video sequence, you have group of pictures containing pictures. Each picture contains now slices, and the slices is constituted of macro blocks. Each macro block is constituted of 6 blocks, 4 for Y, 1 for CB, 1 for CR, and you have inside each block the differential DC coefficient, the variable length coding runs, and until the end. As for the MPEG-2, the MPEG-2 is conceived for higher quality videos at a bit rate that is more than 7 megabits per second. It provides several profiles aimed at different applications. So you choose the profile according to which application you want to use the video inside. Simple, main, signal to noise scalable, specially scalable, high, another chroma subsampling for 2:2, chroma subsampling, or a multi-view. With each profile, you have up to 4 levels that are defined. These are the 4 levels. The DVD video specification allows only for display resolution 720 x 480, 740 x 480, and 352 x 480, and finally 352 x 240, which is a restricted form of MPEG-2 main profile at the main and low levels. Those are tables that show us the profiles and levels in MPEG-2. So you have the simple, the main, SNR, especially high profile and multi-view. And for each profile, you have if the levels are available or not. 4 levels in the main profile of MPEG-2. You can see the main profile. In MPEG-2, you have the 4 levels that are all available, and you have for each the maximum resolution, the maximum frame per second, the maximum pixel per second, and megabits per second, and for which typically application it is used. Some are for film production, some are for consumer HD TV, some are for studio TV, consumer tape equivalent, etc. What does MPEG-2 also does? MPEG-2 must support interlaced video. Until now, no support for interlaced video was accomplished. So MPEG-2 supports interlaced video as well, since this is one of the options for digital broadcast TV and for also high definition TV. So you remember the top field and the bottom field, which are crossed in the frame. You can separate them or you can join them. Okay. In interlaced video, each frame consists of 2 fields, reference to as the top field and the bottom field. If you use the frame picture, this means you join the field. You join the field and you constitute one frame again. So all scan lines from both fields are interleaved to form a single frame, and then it will divide it into 16 times 16 macro block and coding using motion compensation. So each picture and field prediction for field pictures in MPEG-2. Inside A, you can see the frame picture versus, this is the frame picture versus the field pictures. Inside B, you can see the field prediction for field pictures. If you choose the field picture, so you keep each field apart, each field is treated as a separate picture. So the top field will be predicted using the top field, the both fields, and the bottom field will be predicted using both fields also. So each field will be treated as a separate picture, as if it were a separate frame. Zigzag and alternate scans of DCT coefficients for progressive and interlaced video in MPEG-2. You have the traditional zigzag scan, and also in MPEG-2 you have another kind of scans, which is the alternate scans, which is also known to gather the low values of the DCT transform and after the quantization in a one-dimensional vector. Now we will see some major differences from MPEG-1. So a bit by reference to MPEG-1, what are the differences in MPEG-2? They have better resilience to bit errors. It supports now 422 and 444, also chroma subsampling. It has a more restricted slice structure. An MPEG-2 slice must start and end in the same macro block row. The left edge of a picture always starts a new slice, and the longest slice in MPEG can have only one row since they can one slice on one row, the start and end. And it is most flexible. It supports most flexible video format. It supports various picture resolutions are defined by the DVD and ATV and HDTV. Other major differences from MPEG-1, the nonlinear quantization. Two types of scales are allowed in the quantization. The scale that is same as MPEG-1, integer in the range of 1 to 31, as you can see, as you can remember some slides previously in the quantization default matrices. And there is another nonlinear relationship, another option, which is the scale of I can be different of I. For example, the I scale's value can be looked up from the table 11.7 from the textbook. Scale of I equal I until a certain value. From 9 until 31, scale of I differs. So if you have bigger values, you divide by bigger scale, quantize by bigger scales. Another two standards are for ISO are the MPEG-4 and the MPEG-7. I will quickly explain what is the purpose of MPEG-4. You can read them. This is very easy, but you have to know that MPEG-4 is mainly provide a great attention to user interactivity. Not only inside the video, this is linear coding and decoding, there is also interactivity with the user. Okay, and the focus is on, instead of macro block based coding, it can be done over object based coding, which can accomplish higher compression ratio, which is beneficial for digital video. So the version 1 of MPEG-4 was released in 1999. MPEG-4 Part 2 is targeted at low bitrate, but now it can have until 5 kilobits per second, and from 5 kilobits per second until 10 megabits per second. So this is a very big range now, and it is up to 2 megabits per second into some apps. Here in this schema we can see the composition and manipulation and MPEG-4 video, which is video object plane. You can see in MPEG-4 another concept, which is you consider each object in the video alone. So you have video object planes, and with each plane it can make the encoding and decoding and the content-based manipulation easier. You can take one object, rotate, scale, delete. So the manipulation of the video and the interaction is very much easier. As for the MPEG-7, between MPEG-4 and MPEG-7, the effective and efficient audiovisual content-based retrieval was on focus. So in MPEG-7 coding, what is important, that is you can retrieve something, you can retrieve some information, you can retrieve some descriptor from the MPEG-7 video. So you code the descriptors, the descriptor schemes. This is only for your information. You don't have to dig inside this coding. We are only giving the information about this coding, what differs from the previous, what is the focus, why did the standard committee develop this coding. But the main issue, the main concept was in the motion compensation and the IP and B frame types. Next we will see, and finally we will see some some information about the new video coding standards, which are the H.264 and H.265 coding standards. By the joint video team JVT of ISO, IEC, MPEG, and ITU together, the video coding expert group, which is ITU TVCEG, it was released the H.264 in May 2003. It was known also as MPEG-4 Part 10, okay, which refers to the advanced video coding. This coding standard, what does it provide? It provides a higher video coding efficiency. It provides up to 50% better compression than the MPEG-2, up to 30% better than the H.263 and MPEG-4 advanced simple profile, whereas it can provide the same quality of the compressed video. So the compression is bigger, but the quality is the same. It covers a broad range of applications from high bitrate to very low bitrate. You use very low bitrates even when we are in 2020. For example, for smart devices, if you have a smartwatch with a very low resolution, so you need compression codings that are adequate for the low bitrates. Improved core features in the H.264 by reference to the previous standards are the improved core features plus the new coding tools. So there are tools that were not even present, not only improved. It led to significant improvement in the compression ratio. As you can see, it has significantly does a better job. Error resiliency and subjective quality. What is subjective quality? Subjective quality, I will talk about it. Dr. Zan also explained it lately. It is that if you measure the difference between the original and decoded video, you will have a very high difference. But in fact, this difference is due, for example, if you add the value 1 for all the image, it is not perceived by the human eye. So this measure is not used anymore. The subjective quality is sometimes a better measure to see. The subjective quality is that you bring someone to see if the quality is good or not you measure it automatically. So this is subjective according to the opinion of the person. So this leads to better subjective quality. And the default standard for various applications is now the H.264 and then the H.265. That varies from the Blu-ray disc to HDTV broadcast to streaming over the internet, the video, to web software such as Flash and Silverlight, and up to apps on mobile and portable devices. Similar to previous, it is block-based hybrid coding scheme plus motion compensation plus transform coding, and each picture separated into macro blocks, which is 16 times 16 blocks, and arbitrary size slices can group multiple macro blocks into self-contained unit. This is the basic encoder for H.264 advanced video coding. You have, as you can see, new concept, integer transform, not like the DCT transform. You have coder control, scaling, and quantization. You have the input video frame here. It enters. It is divided into 16 times 16 macro blocks. You have the intra-frame prediction, the motion compensation, the motion estimation from one side, and you have the integer transform and scaling quantization and coder control with coder data. So there are new features, new techniques, and then scaling and quantization and inverse integer transform and deep blocking filters. So like these techniques, we will not explain them, but you can see that the encoder of H.264 is more complex than the encoder of the first H.261. The main features of the H.264 are the following. There are integer transform over the blocks of size 4 by 4. The integer transform has a low complexity and has no drifting. In H.264 you also have variable block size motion compensation. You can have the block size 4 to 4 or 16 times 16 and so on in Luma images. You can have what we call the quarter pixel accuracy. Remember in H.261 we have only full unit pixel accuracy for motion vectors. Now we can have quarter pixel accuracy. You can say the motion vector is 2.25, 7.75, for example, in horizontal and vertical displacement. And this can be done by using the interpolation. The multiple reference picture, you can have motion compensation, multiple reference, more than just P or B frames for motion estimation. You have more frame types. And the directional space prediction for the intra frame. You can have now space prediction. We always had spatial prediction for the intra frame, but now you have the directional. The in-loop deblocking filtering, and there are variable length coding, context adaptive and context adaptive binary. So context adaptive variable and length and context adaptive binary arithmetic coding you have. And more robust to data errors and data losses, more flexible in synchronization and switching of video stream produced by different decoders. Decoder in H.264 has 5 major blocks. We already cited them: the entropy decoder, the inverse quantization and transform, the motion compensation or intra-prediction, the reconstructor, and the in-loop deblocking filter in reconstructed pixel. Finally and lastly, let us see the H.265 properties. H is about the high efficiency video coding. This is the latest standard jointly developed by the joint collaborative team, which developed also the H.264 on video coding from the groups ITU and ISO. The final draft was released in January 2013. It was called MPEG-H and also called H.265. The development of this coding standard was motivated by 2 factors. The first one is, of course, the increasing video resolution. We have bigger and bigger video resolution, as you have seen in the chapter of video basics. We have until 8K times 4K in the UHD TV. And the second reason is the speed up by exploiting the parallel processing. Since we now can have parallel processing, we can exploit this to make faster decoders and for higher resolutions. Initial goal was a further reduction of 50% of the size of the compressed video of the H.264, but this initial goal was very easily exceeded. The H.264 and H.265 are currently the leading candidates to carry a whole range of video contents on many potential applications, and these are the default formats for color video. The default format is now the YCBCR, and it is available in main profile. The chroma subsampling is 4:0, and we can have others. The main features of the H.265 are the following: the variable length, the variable block size for motion compensation. You don't have to use 8x8, 16x16. You can use ranging from 4x4 until 64x64 in Luma images. The macro block structure is replaced by some other structure called quad tree. Okay, don't have the macro block structure in these features, in these standards. This quad tree structure of coding blocks at various levels and sizes, so you code the block at different levels. And it can also, the main feature is of course the exploration of the parallel processing already mentioned before. Integer transform is another main feature for in various sizes for 4, 8, 8, 16, 16, 32, 32. And we have improved interpolation methods for the quarter pixel accuracy in the motion vector. Expanded directional spatial prediction for intra-coding. You have now 33 angular direction for directional spatial prediction for intra-coding, and you have a potential use of not the DCT but the DST, which is the discrete sign transform in Luma intracoding. We have also the in-loop filters, including deep locking filter and sample adaptive offset, and you can use only the CABAC and no more CAVLC. So you don't have variable length coding, you only have arithmetic coding. And this was it for the chapter, and this was the final chapter in the multimedia. Now, we still have one chapter, which is Introduction to Image Processing.